you so much. I, yeah, it's a school policy not to. Okay, so, oh, by the way, if you look over here, you'll see that I added a sample final from like many years ago. So, and it doesn't, well, I'll explain it, but you could start looking at that if you want. Um, and turn the video. Uh, why is it not? Okay. And uh, hide. Okay. So upload. You uploaded it, right? Okay. So go ahead.
Is there a way to full screen this? I'm not.
You full? Oh, is it PDF?
Yeah,
Um, so want to make it bigger?
yeah, I guess so.
I'm not sure.
Yeah, I don't.
Okay.
Okay. So my name's Osama. My project was on what is a Gantt chart and how is it useful? So before I get into what it is and how it's useful, I want to get into the history a little bit. And it all started with the Industrial Revolution. And you have all these different industries, you have factories, you have railroads, and you have construction. You have all these different industries that are rapidly increasing, and the amount of work that's being done is just accelerating. And we need to find a way to like visualize the progress, to visualize the delays, keep track of employees, the work that's being done. You have all these different things that need to be tracked, and like how do we do it? So that's the question that we asked back in the 1800s. How do we track all these things at the same time, and how do we manage our resources? How do we manage coordination, teamwork? We asked these questions, and Henry Gantt gave us a solution, which was the Gantt chart. And his idea was to make a chart that lists the tasks vertically, and the timeline would run horizontally in this, as you can see in this picture, the dates at the top and the tasks that are, I'll show you in later slides, and the bars represent the amount of time taken and what the task is. So for example, this was one of the first charts that was made. This is what it, and over time it has since evolved from a paper chart that looks like this to a more interactive digital tool that looks something like this. And you can see those tasks listed there. Planning, research, design, implementation. You can see the dates, January 19th, all these different months, and the amount of time that's taken as the blue bar, and that's also determines like the progress, how much progress is being done. You can tell that by the bar itself. And and over time, it has become a big project management tool, not just for industries, but for software development, which is so. For example, if you're developing a web application, you're going to use this. If you're managing a business, this is what you're going to be using. And it's also used in CPU scheduling, which is an operating system process where you're determining which task gets the access to the CPU. So it's useful for all these things. And again, it's also, you can see what's happening at any point in time, what tasks are in progress. You can set realistic timelines. You can find overlaps, find scheduling conflicts, and fix them accordingly. Um, and you can see which tasks are dependent on another. So you can't finish task, I don't know, B if you're not done with task A. You can't really do that. And you can see that visually. And this is a chart that I made myself. Just show an example. If for example, if you're making a web application, this is probably what it would look like. And I can't really, the picture didn't come out right, but I did the best with what I could with the software that was using online, that whatever one was available to me. So this is one that I made. So for example, if you're doing a web application, you have all these different tasks. You have planning, research, design. You have your implementation, which is the front end development and back end development. And then you also have testing. These are all things that we learned in this class. And so that's what I made as the tasks. And you can clearly see the deadlines here. And the shaded in part is how much progress is being done. And you can clearly see that planning has, you're given a deadline of a week. For research, you're also given a week. For design, you're given a little more. And you can see that front end and back end are both started at the same time. And again, you can visually see all of this. There's a lot of detail. You'll know that you can't start testing, which is the last criteria, if you haven't done the development, the implementation. You can't test something that you haven't yet created. So you can see that here. And if you're reaching a deadline but you haven't made enough progress, you will be aware of it and you can plan accordingly. You can change these things, and you can see it. And yeah, and I believe that's the end of my presentation.
Okay, thank you. Okay. Okay. Very good. Actually, you answered one of my questions. Like, I was gonna ask you, like, is it showing what you wanna do or what you did? Okay. So, okay, who's next? We're doing in class. Hagan first. Okay, so that's here now. Okay, go ahead. Is anybody going to run again? No, I don't think so.
Yeah, so today I'm going to talk about how does a bootcamp course differ from a college course. So in short, the bootcamp course is like shorter and more focused on like practical skills, and college course are like broader and slower, and they're more focusing on our foundational skills. So Um, and next I'm gonna talk about the purpose and time frame. So a bootcamp course is like much shorter, and they're often just weeks or months, and they teach you specific job skills. Um, and for example, like web development and interview practice, and they move fast with less theory. So the goal is to build something usable very quickly compared to college course, which is usually part of a semester system, and it's like connects to a major or degree path, and it's focusing more on theory compared to bootcamp course. So the goal is to build deeper understanding of computer science. Um, and the second difference is about the learning style. So a bootcamp course feels more like training. So it has a very fast pace, and the students usually learn a lot just by practicing and doing uh, and building stuff. And the goal is to make you become comfortable using the skills in a practical way. And a college course is like feels more like academic study. So there will be like lectures, readings, homework, quizzes, exams, etc. And um, so the bootcamp style is like learn by doing the right way, and the college style is more like we understand the concept first, then we apply it. And here is a simple example of learning web development. And Bootcamp is build a small app early, then keep improving it. And the college course is they teach you concepts first, then connect them to like larger assignments. And the next part is about their assignments and assessments. So Bootcamp is like they just lets you do like many projects and portfolio and some practical task. And the college will give you homework, quizzes, midterm, final exams, and you need to treat them very seriously because they will count towards your grade and credits. And if you don't do them well, you might not get the degree. So the final takeaway is you can't just say which one is better. It depends on your needs. So you choose a boot camp if you need like focused practice, like when you already get a degree, and you choose college when you just want to like you don't have a degree yet and you want to enter the field and uh, find a job. So that's my presentation.
Okay, good. Very good. So, one more person, and then we'll have some class, and then we'll do one more. Okay, I don't really have some.
So today I'm going to do two methodologies that you probably heard of, Six Sigma and Agile, and how they specifically differ from each other. On the surface, they sound like frameworks improving on how work gets done. That's true, but how they approach are very completely different. Six Sigma is a data-driven methodology that designed specifically to reduce defects and eliminate variations in system processes. The name itself comes from statistics. Sigma is a measure of standard deviation, and the goal of the Sigma is to reach a level of quality where you have a fewer than 3.4 defects per million opportunity. That's essentially near perfection. To get there, Sigma has to follow a structured step-by-step framework through define, measure, analyze, improve, and control. You can start this by defining the problem, and then you can measure what's happening, analyze and make improvements, and finally put control in its place to make sure the problem doesn't come back. Agile is a very rather than fixing a system process. Agile is an iterative development approach focused on building and delivering working output as quick as possible. Work is broken into short cycles called sprints, usually anywhere from 1 to 4 weeks. At work is broken at the end of each sprint, the team delivers something tangible and useful. The whole point is to get the feedback early and often so you can adjust the course before you spend months going in the wrong direction. Agile places a huge emphasis on collaboration, team communication, and adaptivity. It comes up, yeah.
Yeah, activity.
Yeah, okay.
Okay.
To compare the two, Six Sigma is fundamentally about fixing something that's already broken. You have a process, it's producing errors, and you want to eliminate them. It's driven by data and statistical tools. follows a long and structured project timeline and moves through its steps sequentially. You don't jump around. The entire mindset is about minimizing variation because variation is the enemy of consistency and quality. Agile, on the other hand, is about creating something new and getting getting it right over time. It's driven by continuous feedback, runs on short sprints rather than long phases, and designed to be flexible. Plans can do and do change between sprints based on what the team learns. Whereas Six Sigma treats change as something that's to be controlled, Agile treats change as something to be embraced. Oops, sorry. A really good way to understand the difference is to look at the core question that each methodology is trying to answer. Six Sigma asks, why does this keep going and what does it keep going wrong and how do we eliminate it? And Agile asks, why did the customer need right now and how fast does it deliver? Six Sigma suits for manufacturing, healthcare, banking, stable, repeatable processes, while Agile suits software product development, uncertain involvement processes. So to bring it all together, Six Sigma is something about eliminating defects in existing processes using rigorous data analysis and structured framework. Agile is about building and improving products quickly through short cycles and constant collaboration with the customer. They differ in their goals, their timeline, and their mindset, and their industries they best suited for. Neither is universally better than the other. It really depends on how you want to do your processes.
Kissing they don't really conflict with each other.
Yeah.
Okay, very good. Great. Okay, so we'll do a little bit, finish up for the semester, and then we did most of this stuff on Tuesday, but I'll just finish up. Let me just go. And just put this, switch my glasses. Okay. Okay, that's better. Okay, so where are we up to? Oh yeah, so okay, so I did show you the just for those who weren't here yet, I showed you I had created a new folder called Final Review, and this is where I put already a simple, like I did for the midterm, like a sample. So we'll be going over that soon, probably today, but you could look at it yourself. Okay. Meanwhile, I just wanted to finish up chapter 9, and that'll be it. So, okay, so basically the last chapter, this is the last chapter we're going to be doing, which is really like the introduction, like the basic software engineering, and the rest of our book is more like complicated stuff, like more delves into the real issues. Anyhow, so but chapter 1 through 9 is pretty much what I do at work. So so I think this is pretty good for your job, or potential job, or for a job interview, because I don't think like most people go further than this. Okay, like there's ways to make charts and predictions and stuff like that. So, but we're not getting into that. Okay, so the one of the main issues with maintenance, right? So again, we've done like a lot of stuff, right? The last thing we're doing is we're up to maintenance, right? We did testing, right? And we did architecture, and we did, designing classes, stuff like that. The last thing we're going to do is the maintenance, right? Which is after we do testing, right? We have to keep the software going. So everybody who has any product, anything, right? You always face the problem of what do I do? Do I keep this or throw it out? Does it need to be fixed? Let's say anything you own, right? It has this issue, right? If you have, for example, you have, let's say, um, like, like something silver, you have to decide, do you want it, if you're gonna have to keep on, cleaning it so it looks, it's bright, it does, because the silver over time, or anything, right, it gets full of dust, or, right, it's hard to, so the question always is, when is it time to get rid of it? When should I still take care of it? Right? And so, so that's always the question. The same question applies to software. When the question is like, is it worth it to keep it going, or should we just get a new program? Right? So, and the answer is that um, so so I just gave it different examples. Like, for example, someone has a car that's only 10,000 miles, then it's worth a lot of money. So you probably would want to fix it, right? Um, but and then I could also add features to it, right? And probably if it's a 20-year-old car, I should probably get rid of it, right? It's probably not worth putting money into it. Though nowadays, the new cars are so bad that who knows? Something simple uh, without a million computer chips in it, right? Might be a lot easier to repair and take care of. Um, so basically, when you go to a mechanic now, they're really software engineer. Yeah, they're really computer scientists. Yeah, they're not more than they are fixing anything, right? That more than mechanics. Like they gotta diagnose the chip and why did the person get this warning, and you know, so they're more like people who maintain computers than people who maintain than people who fix things. So that's the way the industry has been going. Um, so okay, so basically, so step number one is that there's always going to be change regarding software, right? So whenever software is written in the back of your mind, you have to always think that this might change. Like for example, I always quote this, but it's actually true, is that there like it used to be for many years that SQL was like the only database around. And that was true for a long, long time. But recently there have been a lot of different types of databases that have been created, like NoSQL databases. I forgot what they're called. There's MongoDB, that's a NoSQL database, and there's another one that it stores the relationship itself. It gets stored. So like I forget what it's called, but it's pretty cool. You could like it could detect. It's good for detecting like relationships between data. So like you could see that uh, people whose teachers study at some university um, that they do better. They're better students, stuff like that. They get higher grades. So it detects it's better. It keeps it's easier to track relationships between the objects. And I forgot the name of the software. It's called Graph software. No, Graph database. I forgot the name. Let me just see if I remember. See, a database that stores relationships between. No, we don't want that one. Uh, uh, no, no, no. Oh, maybe that's a graph database. Graph. I'm trying to think of a specific name, and Yeah, and the edges, right. So, right. So this would be like an example of, oh, that's a new Neo4j. I don't know how popular it is, but like you have all these relationships that are stored, and um, so this is actually a different type of database. I mean, a different way of storing it, right? You're storing the important part is the relationships more than the actual, then we're focused on relationships more than the data. So, for example, you could see that the supplier, most employees, for example, get from the supplier. And you could like sort of see it, even though when relational, you could also do it, but it's more obvious or easier to show with these types of databases. Um, so anyhow, the point I was making is that everything changes. So now that we have this database, somebody at work is going to say, your boss will say, "Hey, let's use this database instead of the one we're using." And you should be you had that in the back of your mind that the like usually if you did like layers of code, so you made a database layer of and so that if you really did it well, you could just swap out the database layer and put a different database uh, on the bottom of your code, right? So so that would be that would be something that actually happens nowadays, right? As new things and the same thing in the other on the top as more ways of displaying data happen. Like now, they have like glasses that could show. I mean, that was a while ago, right? Google had these glasses, right, that you could see things on. So like so you would have software that instead of displaying it on the screen, would have to display it on a pair of glasses. Or now they have cars that have heads-up display, right? So there's different. The technology is changing, and your software has to keep up to it. So again, if you wrote your software that the presentation layer is separate from the rest of the code, then it's easy to swap it out, right? You could just change how it gets presented into a different, by changing a layer. So again, that's something, and probably will change, right? Like so it's always you always have to be in mind that things are always changing, right? You can't like for example, ATMs. Does everybody know that ATMs used to use a software called OS2? Ever heard of OS2? So it was actually at one time. You heard of IBM? No? Okay, one time IBM was the Google of software companies. So they were the big they were IBM was, was the they were the 800-pound gorilla, right? So if you wanted something like there used to be a saying that you could never go wrong with going with IBM, like no one would ever challenge you if you decided to use an IBM product versus another product. In fact, IBM developed the first PC was written by well, I mean first like PC that we use like the because there was an Apple computer, but I think the first PC that used like over the counter, like not over the counter, off the shelf material, that was IBM. So they actually, and happened to be, there was a guy called Bill Gates who sold them a operating system, which he actually bought from someone else. And it was a big lawsuit over and when the guy realized what he gave up. So he actually sold it to IBM and then IBM. So basically, with him was like Apple, their computer has like proprietary software and hardware. So they never had any real competition. But IBM, they use off-the-shelf components because they were in a rush to beat Apple, and they used the software itself was written by someone else. So they basically they basically lost the first PCs were all IBM, but they lost the market because anybody could just build a PC, and the operating system eventually was replaced by Microsoft. So at one time there were two operating systems. There was an IBM one you could get, or you could get one written by Microsoft, and you had a choice. And but eventually, Microsoft just they basically basically IBM lost the market. So the point is that OS/2 was a operating system which was developed at one time by IBM and Microsoft, and it was like the first attempt at I think a 32-bit or 64-bit operating system, and OS/2 stands for Operating System 2. And the idea was that it would be it wouldn't crash, it would be very stable, as opposed to at that time Windows would always crash. So so for a long time, ATMs pretty much all ran OS/2 software. They ran on top of OS/2. So, but then there's been people realized it was never being OS/2 is basically not being changed, and then people realized there was a security flaw in OS/2, and they could get into the ATM somehow and like get it to give dump all the money or something. I forgot what the flaw was, but so basically that forced. So for a long time, banks, all the ATMs were using this old software, right? And then, but eventually, things change, right? People, now they have AI that writes viruses, right? That tries to break into other machines. So as things change, software has to change. That's basically my point. So basically over here, this is I think from the book that you have software development, software evolution, where we change it. Then finally, we're just keeping it around, and then finally we get rid of it. So that's usually the life cycle of software, right? We develop it, we make a few changes, um, and then we eventually just then we keep it around, and then we dump it. So usually software is not going to last forever. Um, and Okay, this is an example of where is it? Okay, I thought I had another diagram. Where is it? Oh, here it is. So basically, a lot of companies um, have what's called legacy systems. And this shows the issues that in other words, it's tempting to say, let's just throw it out, right? But whenever you switch software, there's a lot of pain that goes with it. Why? Because number one, uh, it's expensive, right? But it's expensive to hire programmers or to adopt a new system, or it's much cheaper just not to change. But um, but for example, when you change your software, these are all the issues that you have to think about. Number one, what about my hardware? Am I going to have to get new hardware, right? Or will I have to pay more? Let's say you host your software in the cloud. Will I have to pay for more, like space or whatever, right? Then the other thing is that the biggest problem is over here, which is or these two over here, which is that the usually the software um, it doesn't just have it's not just like some generic type of thing, right? Usually it's something that's specific to your company. So all the policies and the rules are like inside the software. And the people who wrote the software left the company years ago. So if you just dump the software, you don't know why it does what it did. Like you always have this question of, was there a reason for this? or was it, the person who wrote it made a mistake and I could just get rid of it? So basically, so these are the biggest issues, right? That you don't understand. There's no one around like who knows why something was written the way it was. Like I have a friend, he works actually in software test. He used to work for testing software for the space station, and but he was actually also involved. He was there at NASA for a very long time. They actually, like, he was like the person they would ask when they wanted to change anything on the space station. They would go to him because he was there. He was like he knew all the history of everything that went on with the space station. So, um, and so so a lot of companies, they don't have that, right? They don't have the people who originally wrote the program. They left or they retired. And people don't, but meanwhile, they don't understand. We're left with, why is the program doing what it's doing? And it's hard to know if, right. And usually the documentation isn't so great. So that's why this is the major reason why people don't want to just throw out software, because it's hard to know exactly what the software is supposed to do. Because every time there's a change made, right, there's not necessarily a document, a reason why that change was made. And even if there is, who wants to go through all that, you know, go back years and years of of changes and looking why things were changed the way it was. Could be with AI, it might be quicker. Like it'll look and you could ask it like, when was this change made and what did it fix? You know, maybe you could do that. Um, So that would be something that AI would be probably very good at, right? Because, for example, if you use Git, I believe that Claude could go through Git and look at the history, and you could have it search for stuff in your history. It's pretty cool. Um, okay. Okay. So basically, we have, but this is basically what we said, that we have three options what to do, similar to what we said up over here. In other words, you have three options. Basically, you're going to keep it, or you're going to, oh, actually, there's one more option. No, it's one option is to just keep on making small fixes and keep it going, right? As long as possible, maybe till you retire and have someone else worry about it, or you leave the company. So you just do as little as possible, and basically, like, we have a system like that for Microsoft. It basically is the same. It works the same way now that it did, probably, I don't even know how old it is, maybe 20 to 30 years ago. They haven't really changed anything. And now they're just dumping the whole thing and they're replacing with another product altogether. So that's one way, is you just keep the product going. You charge customers for maintenance, even though they probably don't need it. But companies usually just pay for things that they don't need. And then, because they get scared that, no one wants to get blamed for, when the system goes down. Oh, you didn't pay for the upkeep, the maintenance. So you didn't put, you didn't pay the yearly fee for maintenance that some companies charge, or actually most of our companies charge that. Um, okay, that's one option, is just to keep it going until it just finally dies. Um, Another thing to do is do a little bit more aggressive, which is that you actually take you keep the basic software, but you cut out some of the parts to make it more work better. So you're re-engineering the system, or the most is basically is where we just get rid of the whole thing and we're going to replace it with something new. So obviously the safest way is number one, and the and number three is the riskiest one. So basically, three is usually only done when, like, when you really can't the software is really, really in bad shape. Um, um, and this just gives you a way of like, um, this is like a way of like to see what are we, to see if it's worth or if it's worth keeping software or not. So for example, this is 24% of the budget is spent of the maintenance budget is spent, let's say, on in this graph is fixing bugs, uh, which is pretty, whatever, it's just a number. And then 19% is the environment, meaning that, just things change and you have to keep up, like software updates and stuff like that, or operating system changes. Uh, and over here is functionality or modification. So basically, this is actually pretty good, I would think, right? This looks pretty healthy that the only 24% is spent on real issues, on real bugs, and the rest is, either just making it work with other systems or adding functionality. So basically, what you try to do is you try to see what's going to happen in the future based on, I guess, on this graph over here. You want to predict what's going to, um, what are actually, I have another graph. We'll see that you want to try to see, like, like you want to tell management that, for the next, let's say, couple of years, this is what we predict the cost of maintaining the software will be, um, based on what we see now. Of course, right, no one can see the future, so, but based on what we see now, you could tell management, these are the costs we expect now, so management could decide if they want to, what they want to do, right? So, sort of like when you go to mechanic, you say, so you think it'll last for another 20,000 miles? And the guy says, well, you're going to need, in 5,000 miles, you're going to need a new transmission, and 10,000, you're going to need to rebuild something else, right? So you want to basically, so this is the same idea that you want to try to somehow predict, what the costs of the software are going to be in the future. So the management could decide, well, maybe we should start looking for a replacement, right? Or maybe we should re-engineer it. And this is basically saying that um, that over here what they're doing is they're restructuring, they're re-engineering it, and basically the input is the program itself because they're assuming that there's really not a lot of documentation or it might be wrong. So the actual program itself is the document of what you should be doing, what the program should be doing. And then you're basically reverse engineering it, then you're creating the documentation, and then eventually you have a restructured program. But that's basically how it works if you want to re-engineer it. Okay, and then okay, and then this we spoke about last on Tuesday that where is it? The oh, so we said that there's four types basically of maintenance, which is basically corresponds to what we said over here. So over here we had we were fixing the bugs, then we're just maintaining it, and so over here the idea is that we're um, corrective, which means fixing the bugs, and then adaptive is based on the environment, and then perfective is we're adding more. I'm sorry, we're adding more features, right? So and then preventive is basically someone says, this code is really, it's gonna be hard to fix. and no one's going to remember what this code does or why it does it. So we should maybe fix it up. It's like very complicated code. Um, so so that we would do some preventative work. And like I have down here, I think it's an example of preventive, um, like um, does it have an example here? Yeah, like for example, the best like for example documentation. So let's say when the program has changed, and so you want to know like people 5 years from now will know what the program does, why it does what it does. Um, and then you want to always um, update the libraries it works with, right? Because you don't want because basically there's always vulnerabilities found. Like whenever I build code, there's always a warning this code is vulnerable, has known vulnerabilities, and then you could do security audits to make sure that it's still pretty safe. And then um, you want to restructure the code. Now, in practice, people don't want to do code restructuring. And so basically, because that is the most dangerous, and it basically, it's the most, um, there's no, it's from management's viewpoint, there's no gain, right? You tell them, well, we rewrote we restructured the code and it only cost us $500,000. And they'll say, what? So what did I get out of it? Oh, you got better code. So they have no idea what you're talking about, right? You have cleaner code, right? It's easier to maintain. They say, well, it was working fine, and before you, yeah, I don't want to spend them $500,000 on doing that, right? Um, and also there's no real gain from management's perspective, and but there is a loss, right? Because if you rewrite the code and it crashes now, then they're really going to be angry, right? Because not only did you spend money rewriting it, but now you're actually making it worse. So that's all. That's so code restructuring is never very popular in a company because there's no real gain from management perspective, and there is a there is a the risk is more than the gain, right? So again, of course, if you do the other things, there's no real, software update that management understands. You have to keep up with, with security and stuff like that. In fact, a lot of clients, they won't do business with people who, like there are companies who actually validate your software. It's like, for example, let's say someone is giving me their tax returns, right? So it has a lot of confidential information in there, right? So, um, so there are companies which they'll only give you their information if you have like certain certification on your software that it's going to, um, that it's safe and it's secure. Um, okay, I guess we're a little bit running out of time, so I'll just quickly show you the, um, I have these two documents over here, which I thought are very good, but I'll just focus on one or two things here. Basically, um, um, where is it? Oh, here. So these are like, how do you know if your software is well written? So I thought this was really good. So number one is, maybe I'll just copy this and put this into the other document. Um, so, okay, let me just copy this and I'll put this in another document. Uh, okay, so the issue is, um, I'll just put this at the bottom of the file. So, okay. Right. All right. Okay, here we go. Okay, so basically, get rid of that. So basically, you want to know whether your code is maintainable. So these are questions you should be able to answer. Basically, is um, did could in other words, if I find a problem, could I go back and see what changes were made that might have caused that problem? Basically, like use some type of software tool, a versioning tool, where you could go back and and see what code changed and why it changed and how that might have affected it, right? Um, it used to work and now all of a sudden it broke, right? What changed between the versions? Sometimes it wasn't actually like today something happened where somebody told me that this thing broke. It's never broken before. Like, why? I never had a problem before. So it's very funny. So what was the bug? The person used a day instead of typing in 2026, they wrote 2206. So that was like that number, that date was so far in the future, it crashed the system. So I guess I think that was Excel or SQL Server. I guess they won't work in 2206. So there's just a warning out there. There. So basically, could you so do you want to keep track of your changes? Is it easy to change a code? Is it easy to determine what I need to change? Um, and then are the number of such knock-on changes small? I guess it means that if I'm not sure what that means, knock-on of such changes small. Not sure what I'm not gonna. Can I quickly change a change? Can I quickly verify a change? Meaning that, like you have unit tests, right? So, or other testing that you'll see that whether or not the change actually didn't, oh, yeah, right. Is there a way to tell whether it broke? So again, you have tests? If I break something, is it quick? So basically the same idea is that you want to be able to go into the code and make changes and see what's going to happen if you make those changes. And then there's one more document that, let's see, where's the other one? And this one is, I'll upload, but I just want to just a bit, this actually repeats what we just said. And then, it's actually very interesting about, they have like, they said that, like they said, for example, Amazon has software that, where is it? I saw somewhere. They said that Amazon has software that automatically fixes itself. Um, I forgot where it said it, but it's pretty cool. I don't want to, okay, so, uh, okay, so here, so these are more ideas like here. So basically this idea, I'll just put this in here, which is number one, conduct regular updates, invest in quality assurance, which is really what's quality assurance. It's a little bit different. It's Six Sigma. Ensure proper documentation, testing procedures, performance optimization. Always think about, is there a way I can make it go faster? And then these are things that people don't always think about, is that how I monitor the software, right? In other words, I should be able to see if it's running into problems before it actually crashes, right? Like maybe it's going like something was working really well, but after a year, it might start slowing down because of database issues, or I didn't actually, the data wasn't designed, it wasn't designed for the way it's being used. Meaning like I have to create indexes, maybe I have to split up tables, stuff like that. Prioritize technical reduction and receive user feedback. So these are all things that help you maintain the software. And with that, we are done and with this semester and with all the material. And now we're going to have some more presentations. And I guess on next week we'll do the final review, but you can look at it over the weekend. Okay. And also this chapter 9 is not on this review. I have to add it. So, when I created this test, I didn't include chapter 9. So, okay. So meanwhile, let's just have some presentation. Who's next? Okay, you're next. It's order of when you came into class. So who came in, okay, who's next? You came into class? Okay, okay, so, um, um, oh well, here we go. Um, okay, so the internet got slow. Um, Now we have an issue, it slowed down, right? Why did it slow down? Uh, um, okay, here we go. Okay, yeah, please.
Okay. Hello, everyone. My name is Fariha Wahid, and today I'll be presenting on the architecture of high-frequency trading systems, also known as HFT systems. The core idea behind HFT is simple. Speed creates competitive advantages. The faster a trading system can process information and send orders, the more profitable it can become. So what is HFT? High frequency trading uses algorithms to automatically buy and sell financial assets at extremely high speeds. One important concept is co-location. HFT firms place their servers physically close to exchange servers in the same data centers. This reduces latency, which is the communication delay between systems. Another major concept is ultra low latency. HFT systems are designed so that trading decisions happen faster than human reaction time, often within microseconds. These systems also have a very high turnover, meaning they execute thousands or even millions of trades very quickly. Finally, HFT focuses on short-term opportunities. These algorithms try to capture tiny market inefficiency that may only exist for a fraction of a second. So this slide shows the overall architecture of an HFT system. So the process begins in the exchanges and sends the market into the system to the incoming gateway. And then the book builder then reconstructs the market order book in real time. Next, the Strategy engine analyzes the data and decides whether to buy, sell, cancel, or modify the order. And then orders move to the order manager, which validates and tracks them before sending them out through the outgoing gateway to the exchange. At the same time, monitoring and control systems track system performance, precisions, and risk exposure. The entire architecture is optimized to minimize latency at every stage. So, the strategy engine is considered the brain of the HFT system because it makes all trading decisions in real time. Different HFT firms use different trading strategy. For example, market making profits from the bid-ask spread by continuously placing buy and sell orders. Statistically, arbitrage identifies temporary price difference between correlated assets. Latency arbitrage takes advantage of reacting to market changes faster than competitors. Mean reversion assumes prices eventually move back toward their average value. This strategy engine constantly decide, should we buy? Should we sell? Should we cancel? How much should we trade and what price? All of these decisions must happen extremely quickly with minimal delay. Even though HFT systems focus on speed, they also require strong risk management controls. Positions limit prevent the system from taking excessively large positions. Fat finger checks prevent accidental trades at absurd prices caused by software bugs or incorrect inputs. Max loss limits automatically stop trading if losses become too large. Exposure checks monitor total market exposure. And kill switches allow emergency shutdowns if the system behaves abnormally. These controls are critical because even a small software bug in HFT can create catastrophic financial losses within seconds. So while speed is important, safety and predictable system behavior are equally important. So why does speed matter? Speed is everything in high-frequency trading. Arbitrage opportunity may only exist for microseconds, so faster systems can react before competitors. Speed also reduces slippage, meaning there is less price movement between placing and executing an order. To achieve ultra-fast performance, HFT firms uses technology such as FPGA hardware acceleration, co-location, and deterministic event-driven architecture. HFT firms also profit through market making by capturing very small bid-ask spread across huge number of trades. The main takeaway is that high-frequency trading speed is simply a performance optimization. Speed is not simply a performance optimization. It is a requirement for profitability and survival.
Yeah, I think you lose all your money in a couple of 1 minute. Yeah, I was thinking about that when you think, wow, you could lose all your money, right? Yeah, like without, you have to wake up. 1 minute, you have $1 million, then the next minute, you lost. Yeah. Scary. Okay, thank you.
Okay, so my name is Yahir. Today we're going to be talking about how AI is transforming the fintech industry. So financial technology or fintech is basically the process of improving or automating financial services via technology. In recent times, industries kind of like decided to move past those automations and decided to work more with AI workflow. So we're gonna discuss a little bit of that here. So fraud detection and security. So traditional statistic rules, that's essentially forgot the traditional statistic rules is essentially these are processes or methods in determining or engaging certain risks or behavioral causes in in sorry, I apologize. It's basically detecting, well, okay, for the solution here for traditional statistic rules is essentially introducing behavioral biometrics, which is essentially thinking about like if, for example, whenever you use like your phone or whatever bit of technology, like there's certain gestures or things that you do and how you interact with the technology around you. So if, for example, like if one day someone has access to your phone and the certain gestures that you use on that device or whatever is not the same as yours, AI can sort of detect whether that person is exactly you or not. So we can implement sort of some kind of biometrics like keystroke dynamics or scrolling patterns. If any of those patterns that the other person has is different from whatever you have, then we can usually detect that the person is impersonating you. You can also add geospatial anomalies, which is just the fancy way of saying like certain geographical patterns. So like maybe the location of where you are is is important. Like maybe one day you're in New York and then the next day you decide to go to Spain, but AI is kind of worried or whatever, so they might block whatever kind of thing that you do on your phone at that moment. Hyper personalization is a business strategy that kind of uses some kind of technology or software in order to produce like these products or services for like an individual based on individuals and their characteristics. So there's this thing called the segment of one, which is removing broad one-size-fit-all bankings that can juice robo advisors, which they can automate portfolio management for an individual and also introduce emotional discipline layers. So if I don't know, if one day like the stock market is about to drop for something, then AI can introduce some kind of investor to make sure that they don't like sell whatever you have right away. So that kind of gets rid of like the emotional bias that someone may have and adds that layer of protection as well. Um, It's a blueprint that we can use within the industry. So scalability, we don't really have to worry about like in a certain amount of people. Maybe we need like, before using AI, it's not so much before using AI, we probably have to worry about, the kind of people that we need in order to make certain decisions or whatever. So with the use of AI now, we don't have to really sort of worry about that. It's just accounted for with the how we use algorithms and how often we use them iteratively. Orchestration. So AI has kind of become this uh, sentiment that uh, or this active tissue that uh, it's become the sediment or tissue that between large disparate data pools and settlement rails, data pools being some source or some source of thing that's gaining information from various other resources or whatever, and sediment rails being uh, some kind of I guess infrastructure of where how money or payments are made between source A and source B. So AI can really become a useful tool in that sense too as well. So for the future of financial tech, I think it doesn't come as a surprise that AI is much more than just a feature. It's more of an operating system or a vehicle for a lot for companies to use. We can with AI, we're able to kind of ditch using all of those traditional rule-based systems and rely on more self-learning models that are usually scalable throughout time and time. And allowing that integration is also allowing for fintech to move from reactive processing and to predictive intelligence. And yeah, that's my presentation.
I said, I would also like like when someone applies for a loan, like the speed at which they type in the request, the numbers, shows whether
Yeah,
they could afford to pay it back.
yeah.
Or, and also like, people whose battery is low, they found if they don't take care of their phone battery, then they're probably not gonna have a loan.
Yeah,
They're a low risk.
that's true. Yeah.
Crazy things like that. And who's that? Anybody else?
Hey everybody, my name is Galib Mukhtasin. Today I'm going to talk about the limitation of automated testing. So first, what is automated testing? So it's basically testing a software using using a software uh, with like writing a script, making like the choosing the infrastructure, and also it also basically it helps like catches bug like early automatically instead of a human testing every feature, every functionality of the software manually. But it's not perfect. If we do not understand its limit, we risk like building software on top of a false sense of security. There are five key elements of the limitation of a automated testing, which are like cost, judgment, vision, confidence, and lastly, the velocity. For the cost being automated tests are basically are not free. You have to pay in both like in money wise and also time wise. Uh, it takes time to into like choosing frameworks, building infrastructure, and scripting every scenario. The cost of the maintenance, it actually like you have to pay this both early stage of the software development and also the later stage of the software development. Each like UI tweaks, every UI, sorry, API shift breaks is something. Teams can end up like spending more time fixing the old test than writing the new one without a long-term commitment to upkeep. This becomes a burden rather than a benefit. Now we're going to talk about the judgment. It basically talks about how like the automated testing is basically checks the expected behavior. Um, like input goes in, expected output comes out. Real users like realize Windows paste odd characters and double click buttons were never like meant for it. Um, it also can be confusing sometimes. Uh, and like the script like it verifies the behavior, and I think only the human can judge the experience better than a automated testing. Now I'm going to talk about the vision, which I feel like one of the biggest like limitation of automated testing. um, so every like a button can render past every assertion and it still look completely wrong. Overlapping text, broken layout, the wrong color on a like particular browser. Traditional tests like inspect the code, not what the user actually sees. So I'm gonna talk about my own experience of like doing software engineering to build an app for a client in my work. So last year I was building a MVP app, and while making it, there is in Cloud Code there is a MCP server called Playwright MCP method. So what it does basically, it gives eyes to the AI agents. so that it can actually see its output, like what it's actually creating, rather than only the code base. It's the same problem is with the automated testing. It cannot see what it's creating at the end of the day. It can only like see its own code base. And while making that playwright MCP method, even though I spent like a lot of hours, got help from AI, it when it like started running on the Chromium browser, to see to check like every functionality, if everything's working on that app, it started crashing every every 30 seconds or 40 seconds after it started. So I tried multiple times like fixing this, but at the end of the day, I had to abandon that strategy, and instead taking screenshot by myself, checking the console log, and putting it to the Claude Code to fix to find a bug and fix it at the end of the day. Um, so yeah, now I'm going to talk about the confidence. The automated testing, it can test a lot of things, the code bases, according to what we write on the script, but sometimes and it can also achieve like 100% coverage, and but it still can miss like edge cases, race conditions, and security holes. Automated tests only catch what you thought to test. They say nothing about what you forgot. Now, the lastly is the velocity. Um, Automated tests are good for like waterfall method, where the client, they give you a product requirement like at the start of at the beginning of the project, and that's the only requirement, and it's not going to change down the line. That for those type of cases, automated testing are really good. But for like the software engineering method, like agile methodology, it's actually bad, because like with every changes to either functionality or UI or anything else, like every time there is a change, you need to also change the test case. You need to change the scripts. This takes a lot of time, and at the end of the day, like automation works best in stable systems with well-defined behavior. In volatile environment like agile methodology, targeted manual testing and lightweight smoke test usually gives a better result than the automated testing. So with that all said, automated testing is powerful, but it's not the silver bullet. So cost, it requires maintenance. For the judgment, it actually doesn't follow the scripts all the time. Vision, like it cannot see what it's creating. Confidence, it's not correct all the time. And for the velocity, it only works good for the waterfall methodology. Thank you.
Yeah. What tool do you use at work?
Huh?
What tool do you use for the testing?
That's a Claude Code. Inside of that, so MCP are the connectors. Like it basically helps you connect to other apps or any other MCP server. So that's the name of that one. I talked about is playwright MCP method.
Okay.
So that's playwright. MCP are basically connectors.
What?
Basically they are the connectors. They connect other like services with your code bases.
Okay.
Thank you.
Cool. Very cool. Okay.
Okay, hello.
Oh, we just joined about that.
My topic is the benefits of SQL databases versus MongoDB. And this is a topic that is in CS 331 that we take here. And that class focuses on both of these. And we use stuff like we show relationships, and we do like from, select, on, like stuff like that in SQL, and MongoDB is different, and I will explain like the benefits of both of them and which one is better for software engineers in the end. So first we have what is a SQL database? Here I have a picture that shows like examples right here. MySQL, PostgreSQL, Oracle, and Microsoft SQL. They're all connected and it stores data in tables using rows and columns, which makes it structured and organized. And of course, it uses SQL. And here's an example table. The rows show like records, and the column has like information like student ID, name, and major, while the rows is like 101 John CS. This is for MongoDB. It uses data as documents and a JSON format. It has a flexible structure and different documents can have different fields. As you can see from the example, it's different from the SQL database, the structure. This is basically a summary of SQL and MongoDB, what I just talked about, where SQL is tables, fixed schema, and strong relationships, while MongoDB is documents, flexible for schema and data. So I have 4 benefits here, but I have a lot of it's very in-depth, so I'm gonna go over it briefly. So I have 4 benefits listed: reliability, relationships, structured data, and powerful querying. So for the first benefit, SQL, it follows ACID, which is atomicity, consistency, isolation, and durability. And we have 4 examples that it's important for, and it's very crucial for stuff that you can't make mistakes on. This is what I explained in the beginning with the from and select join. It uses primary keys, foreign keys, and joins. We have the structure. The benefits of SQL structure is it prevents invalid data. It's easier to maintain, and for large teams and debugging, it's easier. And here we also have powerful querying. It has filtering, sorting, aggregation, and complex joins. And then we also have advantages of MongoDB. So the difference is that it's good for social media apps and rapid development and large data sets. Okay, so my first example, it has a social media profile where we have 2 different people and they have different structures. As you can see, John has hobbies, gaming and music, while Sarah just has pets, and also John has followers. And also you can come back as a software developer to change the stuff, and it's very easy. Okay, second is scalability and for big data. So the benefits are that it has distributed scaling, it can handle massive data sets, and it's good for cloud applications. Also, it's useful for social media and streaming platforms, which I believe that also I talked about here. You know, uh, in the beginning here. But yeah, here I have a real world examples, which is basically from the beginning slides. You see the differences in SQL and MongoDB and which one it's better in, but I'd say like there's no better choice between SQL and MongoDB. It just depends on like what applications are being made and what's popular and important in today's day. So this is basically a conclusion which has all the benefits of both of them, SQL and MongoDB, And I also just said that the final point is that neither of the database is better, and they need to choose which one is better based on the application that's being made. Thank you.
Anybody next? Okay. Wow, it's late. Okay, go. Two more people? Just 5 minutes though. It's getting late. It is late.
Hi everyone, my name is Shamiha, and I'm going to be discussing the pros and cons of a coding bootcamp. So firstly, what is a coding bootcamp? It is a short intensive training program that is goal-oriented to make sure that you have a head start or a career ready in the tech industry through networking and practical programming skills. It's a degree alternative that can also be a quite significant investment. So the pros are, it is less expensive compared to a traditional degree, as in due to the duration of a boot camp, which is can last until a few months, compared to a traditional college path, which can last 4 years or more. In addition, there's in-demand skills because these boot camps are designed for the modern industry, while they also have few admission requirements, making them more accessible to the general public. However, these boot camps offer narrow expertise. Their course load is limited, and they don't provide the depth that a college education can, such as theory or ethics. And they also lack regulation and financial aid. So where your college can be accredited and can offer you financial aid, significantly helping you to pursue your education, a boot camp is a personal investment, which requires your own money, and you are not always sure of the quality of education that you will be receiving compared to the credibility of the institutions that are set up right now. And currently, it is a very saturated job market. So even if you do invest in a boot camp, there is no guarantee that there will be quite a significant return on your investment, as the job market is overly saturated with because it is such an accessible field. However, with less opportunities and more competition. Thank you.
Okay, very good. I would also add that with the boot camp, they're training you with the current technology. So if you don't get a job right away, then what they teach you won't be good anymore.
Outdated.
It'll become outdated. They're only teaching you what's right now popular. I hope, you know, you know, they're at least that much they're doing. I hope you would help.
All right, hi everyone. My name is Aisha, and my project is about what is a compiler and what does it do. So imagine you speak English, but someone else speaks only Mandarin. You need a translator to convert what to say into something they can understand, and a compiler does exactly that. It is a special program that reads source code written in a high-level programming language and translates it into a machine code or binary that the computer understands or your CPU understands. So when you write code in Python, Java, or C++, and etc., you're writing in a language that's readable to humans, but your CPU has no idea what if, while, or print means. It can only understand binary. The computer's job is to take your human readable code and translate it into machine code before it ever runs. Yeah. There are 4 phases in the compiling. And the first one is the lexical analysis. So it reads your code word by word and breaks it into tokens. Think of it like identifying the individual words in a sentence. It spots keywords if, for, symbols like equal to, plus, and variable names. The second part is syntax analysis. It checks if your code is grammatically correct. Just like dog that ran is a grammatically wrong sentence in English, equals to x5 is a grammatically wrong sentence in code. So it builds a parse tree to map out the structure. Then comes the semantic analysis. Here it checks if it makes sense. So sometimes grammar in a sentence can be correct, but meaning can still be wrong. Things like adding a number to a string. So this phase catches type errors and undefined variables. And then the last one is code generation and optimization. Finally, it generates the machine code. Here it also optimizes, making your code run faster and use less memory. Why do compilers matter? Because they bridge the gap. So without compilers, programmers would need to write directly in binary or assembly, which is an extremely tedious and error-prone process. Compilers let humans write code in human-readable languages and then translate it into machine-readable. It is also portable, so you can write one program in C++ and compile it for Windows, Mac, and Linux. By targeting different compilers or platforms, the same source code reaches multiple hardware types. Then there's also error detection. Before runtime compilers catches syntax and type errors before your program ever runs. This saves time, and it's far better to get a compile time error than have your program crash in production. And then also code optimization. Modern compilers are very smart, and they rearrange your code and eliminate redundant operations and produce machine code that often runs faster than what you wrote initially. Thank you.
Okay. That's it, right? Okay. Thank you. Okay, so we'll start the way I think about it is that on Tuesday we'll go over the sample final, and then I hope they add some stuff about chapter 9 to it before Tuesday, and then maybe the Sunday before the test. I know it's Memorial Day weekend, but if people are interested, maybe we'll have a little bit more review. Yeah, so I think that would be the best for me at least. Yeah, so and it'll be like 2 days before the final, so then so you won't forget, hopefully. Right. Okay. So see you next week, and thank you all for coming to it. Okay.
The finals on the 26th, right?
Yeah, the day after Memorial Day.
Oh, will Tuesday's review be in person or on Zoom? Like
Yeah,
we-
it's both.